हेलो, हेलो, गुड इवनिंग सर। सर मैं ये पूछा था कि मैंने जैसे असाइनमेंट्स जो टेस्ट हो रहे थे तो उनमें से मैंने कुछ मिस कर दिए हैं। तो वो वापस से रिटर्न टेस्ट नहीं दे सकता मैं? ओ, थैंक यू सर। Actually, I am unable to log in the NPTEL site. I don't know why. Whenever I try to log in, it says that your ID has been logged out and something like that only. कुछ ऐसा मेल आता है।
Okay, so I'm sorry. I was saying that I won't be able to help you with the technical aspects over here, and I think you need to take it up with the NPTEL people. I don't think I can help you here. I'm sorry.
Okay, no problem. Already I have sent the mail to them. They are not replying me back.
I see. To what ID did you reply? I sent the mail.
They are not replying me.
To what email ID did you
Uh,
send the?
वेट मैंने सर्च किया था कहाँ से? गूगल से।
Uh,
NPTEL हेल्पलाइन मेल, समथिंग लाइक दैट।
I see. Um, yeah, NPTEL. Yeah, that would basically. Hold on one second. Let me just help you out here. Yeah, you can write a mail to support at nptl.ietm.ac.
सपोर्ट NPTEL, ओके।
You can one thing you can do is let me see.
On that time my fourth semester exam was going on now.
I see. So let me
Now
just
I am
show
in
you.
fifth.
Yeah, let me show you this now. Can you see my screen?
Hmm.
Yeah. So you'll have the fluid mechanics course that's over here, right?
Okay.
Just go here. So I am helpline support and select NPTL. You'll get sorry, yeah, NPTL. You'll get the email ID support at NPTL at that dot
I have
IAC dot.
taken this screenshot.
So you can try sending a mail to that mail ID. Maybe they can help you.
Okay. I am alone in this session.
Yeah, I think generally people don't join this unless they have a query. If you have any query, you can ask. Otherwise, I just
You can end this meeting. I have already done this chapter.
yeah, sure, sure. You can feel free to leave if you don't have any questions.
Thank you. Can I leave now?
Yeah.
Okay.
Okay, so sorry for the delay in starting the session. Let's now get started with the live session. I am Sankaraj. I'll be your teaching assistant for the course Fluid and Particle Mechanics offered on NPTEL powered by SWAYAM. This course is offered by Professor Sumesh and Professor Basavaraj. And for this week, we'll be discussing the week 6 assignments and a few questions, practice problems from week 7 as well. So, with that, welcome, and we'll start with the questions. Consider a spherical particle of diameter dp of mass m moving through a fluid in one dimension under the action of gravity with a constant velocity u. Assume the density of the fluid to be rho and the density of the particle to be rho p. The viscosity of the fluid is mu. And we need to figure out the force of gravity that is acting on the particle. This is very straightforward question. Any answers? Yeah, the correct answer is mg, because the particle is m and moving under the influence of gravity g. Therefore, the correct answer is mg. This is very straightforward question. There's nothing much to think about here. Second question is, what is the saying writer that's given over here? Then they asked, what is the buoyancy force acting on the particle? And we know that the buoyancy force is basically the upward force that is exerted by the fluid on the solid, and that uh, is basically equivalent to, by Archimedes principle, the the volume of fluid displaced equal to the mass times the density. So the volume of fluid is equal to the mass times density. So the volume of so the buoyant force acting here will be equal to the volume of fluid, which is given by mass times density of the particle, sorry, density times g, and this has to be divided with the particle density. So the correct answer is option D. So this is volume times gravity times divided by density of particle. Next, the drag force acting on the particle. So for this case, what we also have to assume is, we have to assume that it is in the low Reynolds number regime, and it obeys Stokes law. Although that statement is not explicitly given, we can use that statement here. Therefore, the correct answer is the drag force acting on the particle is 3 pi mu times u times dp. Okay, if you have any questions, please feel free to let me know. I'll just hang on for a second so that you guys have a time to catch up. Yeah. Okay, we'll move on to the next set of questions. Question number 4, which has another writing material to written up material before answering the questions. Okay, so next question is, consider a spherical particle of diameter dp of mass m moving through the fluid in one dimension under the action of centrifugal force. This is the most important thing. Assume r to be the radius of the path of the particle and omega to the angular velocity in radians per second with a constant velocity u. Assume the density of the fluid to be rho, the density of the particle to be rho p, and the fluid viscosity is mu. Force of gravity acting on the particle is basically, it's not the force of gravity that's acting, that should be equal to zero. It's the force of actually the force of centrifugal force, or whatever you want to call it. And the centrifugal force is given by m u square by r, and we know that u is equal to r times omega, so it will be m r square omega square by r, which we'll finally get it as m r omega square. Therefore the correct answer is option A, m r omega square. Next, the buoyancy force acting on the particle is question mark. It is very similar to what we had done over there. What we did there, the previous question, question number 2, was to take a look at the gravity, which is gravitational force of gravity, which is given by mg, multiplied with the fluid density rho and divided with the particle density rho p. And this is very similar to that over here, where the buoyancy force acting on the particle is basically the centrifugal force, which is given by m r omega square, multiplied with the fluid density to the particle density. Sorry. And this answer is given in option E. Therefore, the correct answer is option E. Okay, moving on to question 6. We have to calculate the drag force on the particle. Again, the drag force equation will in the assume that, again we have to assume that the low Reynolds number limit is applicable and Stokes law is valid. Therefore, the drag force will effectively be the same, which is 3 pi mu times u times dp. I'll wait for a minute for if you have any doubts, so I'll just hold on and charge my stylus as well. Okay, let's look at the next question, question number 7, wherein it's given that a spherical particle of zero point 0.1 millimeter diameter made of steel, density is 7870, falls under gravity at terminal conditions through a liquid of density 820 kilogram per meter cube in a very large diameter tube. The viscosity of the liquid is 10 millinewton second per meter square. Calculate the terminal settling velocity of the particle in SI units. Now, first, in order to solve the problem, you need to find out what region this comes under. That can do this multiple ways. You can just find out the Reynolds number, check if it's less than 1, then we can say if it is Stokes law regime or Newton's law regime, or we can just go and calculate the k factor or the k parameter that is used here. So let's first find out the Reynolds number, if we can, since that is easier to calculate, and that is given by rho v d bottom time by rho v d by mu. But for that we need the particle velocity. Therefore, we can't do that. Therefore, we find the parameter k, which is g dp cube times rho p minus rho times rho by mu squared to the power 1/3. If you were to substitute the values, g is uh, 9.81 times dp cube is 0.0001 cube times rho p minus rho refers to 7,870 minus 820 times rho is 820 divided by mu square, that is 10 millinewton seconds per meter square, which comes out to 0.01 Newton second per meter square, and that squared value is also there, and we just need to raise it to the power 1 by 3. So what I've just substituted, what I've just told, I'll just substitute here and find it out. It's 9.81 times 0.0001 1 cube times 7870 minus 820 times 820 divided by 0.01 square, the whole raised to 1 by 3. And if you substitute this values correctly, we'll get the value of 0.827, which is which is less than so what I want to say here, it is less than 68.9, implying it is Stokes regime. And in the Stokes regime, the velocity of a particle, the terminal settling velocity of a particle is given by g dp square rho p minus rho by 18 mu. And if you were to substitute the values, we'll get 9.81 times 0.0001 square times 7870 minus 820 by 18 times 0.01. We'll get this answer as 0.0038 meters per second. Okay, let's move forward with the next question. And the same write-up is given here. Therefore, we can go ahead and start the calculation of the Reynolds number, which is given by rho v rho u d. And the density is 7870 times 0.0038 times diameter is 10 raised to minus 4 by viscosity is 0.01. We'll get this as 0.299. Okay, so let's move on to question number 9, which has been used to characterize the particle, calculate the parameter k from the details given. So it's given that a sphere of diameter 0.1 millimeter and density 2.8 gram per centimeter cube is allowed to settle under the action of centrifugal force such that the acceleration is 50 g, where g is the acceleration due to gravity. The density and the viscosity in which the particle settles is 0.996 gram per centimeter cube and 0.00801 poise. So the thing to note here is it's everything is given the CGS unit. We need to convert that to the SI unit, and we just need to calculate the parameter K, which can be found out as per whatever I've discussed here, which is uh, G dp cube rho p minus rho times rho by mu square to the power 1 3. And if I substitute the values, I'll get it as 9.81 times 10 raised to minus, okay, 0.0001 cube times, uh, sorry, this small mistake here done here is the gravity is not g, it is in fact 50 g. Therefore, we have to factor in that account, where 50 times 9.81 times 0.0001 cube times rho p minus rho refers to the difference in the particles density, that is 2800, minus fluid density, which is 996 in the SI units, times 996 divided by mu square, which is 0.00801, which is 0.00801 square times 10 raised to minus 4, and this is raised to the power 1 3. Sorry, there is a small mistake. This is 10 raised to minus 2, or we can write this as 0.0000801 square in the SI units, and you will get this value uh, to be equal to 11.11. although the correct answer that is given in the question, although the answer that is given on the website is different from my answer, because I think the gravity that is given here is actually 50 times g, not just g. If you substitute just g into the equation, you'll get the answer that is given in the NPTEL website. Okay. Okay, let's move on to the next question. If you have understood this, which is to calculate the terminal settling velocity of the particle in the SI unit. So what we have understood is k factor is comes to around 11.11, therefore it is well less than 68.9, implying that the Stokes law is valid here. Therefore, the terminal settling velocity in the Stokes regime is given by ut is equal to gdp square rho p minus rho by 18 mu. And when you substitute the values, it comes out to, sorry, this is not 9.81, this is 50 times 9.81 times 0.0001 square times 2800 minus 996 divided by 18 times mu, that is 0.000801. And this value for me has comes out to 0.613. meters per second. Okay, let's take a look at some of the practice problems that I prepared for this week, that has been given in the NPTEL website. These are the non-graded assignments that are there uploaded as the class lecture. So we just first question we have to match the following, and we have certain uh, descriptions or notations that have been used here. So we need to find out how each of them are related to each of these on the left side are related to each of these on the right side. So obviously we can know that not every one answer does not one option does not have multiple answers, just as one answer. Therefore, let's look at the first question, which is given the Stokes settling velocity. And we know that the Stokes settling velocity is ut is given by g dp square rho p minus rho by 18 nu. What you need to understand is in the Stokes regime, the viscosity is important, and the correct answer that matches this is in fact this over here, option 10. Therefore, A is x or 10. And similarly, in the this is for the Stokes. Then similarly for the Newtons, ut is given by 1.75 times root dp rho p minus rho times g by rho, which is in the Newton's regime. And what is interesting is for the Newton's regime, the density is more important than the viscosity. Here there is a viscosity term, here there is a density term. And the correct answer that matches this expression is 1. Therefore, B is 1. Stokes-Einstein relation, which relates the Stokes-Einstein relation relates diffusivity to the viscosity, and So what there is a mistake in the question that is being given, because this D refers to the diffusivity, while in the question is given that D stands for diameter. Therefore, the correct answer is 7 over here. Next, what is the Einstein theory of diffusivity? It means that the at limit t tends to infinity, r square of delta t should be equal to 6 times d times t. Therefore, the correct answer for D is 2, and the Brownian force is given by uh, this relation, which is the ratio of thermal energy to the size of the particles, kBT by Rp. Energy per length is force, therefore the thermal energy to the hydrodynamic particle radius or the size of the particle will give the Brownian force, and therefore the correct answer is for E is 8. Okay, let's move on to the next question, which is given by estimate the largest size diameter of particle of density 2000 kilogram per meter cube, which would be expected to obey Stokes settling law in air of density 1.2 kilogram per meter cube and viscosity of 18 into 10 raised to minus 6 Pascal second. Report your answer in microns or micrometer. So first we start by how do we do this question? We need to think about how to solve this question. So we know that Stokes' law regime can be identified with the help of the K parameter. Therefore, the K parameter is less than 68.9. We know that it is in the Stokes regime, and if it is greater than 68.9, it obeys Newton's regime for until another K value. Therefore, with this information 68.9, we know that K is given by uh, K is G dP cube rho P minus rho times rho by mu square to the power one third is in fact 68.9. And we saw that the K is proportional to dP cube. Therefore, the maximum value of K will give the maximum value of diameter. And from here, we can just directly calculate the diameter of the particles. If we are substituting the values, it will be 9.81 times uh, dp cube times, since we are finding out dp cube times 2000 minus 1.2 times 1.2 divided by 18 into 10 raised to minus 6 square to the whole power one third is equal to 68.9. We just need to find out dp and write it in microns. And the value of dp will come out to be around 1651. I think this answer is wrong because I don't know where I'm making the mistake, because the answer 1600 650 meters is very large particle, which is basically 1.6 millimeter particle that will settle in the Stokes law regime. But I don't know where exactly I am making a mistake. So if anyone finds out and thinks they know the answer, please let me know. Okay, we have a few more practice questions from. Let's start with week 5, where this said that during World War II, Sir Geoffrey Taylor of British fluid dynamics used dimensional analysis to estimate the wave speed of an atomic bomb explosion. He assumed that the blast wave radius r was a function of energy E, air density rho, and time t. Used dimensional analysis to show how wave radius must vary with time. So what happened is we have to check how the wave radius r is a function of uh, how we just have to find a pi variable. This is from week 5, so we are dealing with non-dimensional analysis. So we have to find how wave radius r relates to the energy released E, air density rho, and time t as a raised to b, c, a, b, and c. And we know that the dimensionality of or radius r is L, the energy is ml square t raised to minus 2, and this is raised to the power a, so everything will raise to the power a. Rho is m raised to b, l raised to minus 3b. Time is t raised to the power c. Therefore, we have to club all the equations together. This is 1 plus 2a minus 3b m power a plus b t power minus 2a plus c. Therefore, we have the following equations: 2 minus 3b plus 1 equal to 0, a plus b equal to 0, and minus 2a plus c is equal to 0. From here, we get the expression, we get the values for a, b, and c. We'll get b equal to 1 by 5, a is equal to minus 1 by 5, and c should be equal to minus 2 by 5. So basically what we get is r is proportion r times uh, yeah, r times energy times 1 by 5, sorry, minus 1 by 5, density times 1 by 5, and time times minus 2 by 5 is the pi variable. So we can say that r is proportional to t to the power 2/5, which means that as the radius, as the time progresses, the blast wave radius keeps on increasing, which makes sense. And this question I have just put it because of the recent movie Oppenheimer, where they showed how uh, the atomic bomb was made. So I'm sure this was done at contemporarily that time, along with that work. Okay, I'll move on to the next question, which is on settling, which means that in the question it is given that particles are spherulite at the specific gravity is 4, are settling under the influence of the force of gravity in CCl4 at 20 degrees Celsius, which has specific gravity of 1.594. The diameter of the spherulite particles is 0.1 millimeter. The volume fraction of CCl4 is 0.2. What is the velocity of spherulite? Therefore, all we have to do is first calculate the criteria in which it is resettling, which is given by k equal to GdP cube rho p minus rho by times rho by mu square to the power 1/3. Now, if we substitute this will be 9.81 times 0.0001 cube times 4000 minus 1594 times 1594 by mu square. It will be viscosity of CCl4 is 0.965 centipoise. So mu will be equal to 0.965 square times 10 raised to 3. Sorry, 10 raised to minus 6. We'll get this k value to be equal to 3.4313. Therefore, we know that this is now in the Stokes regime, and the settling velocity is ut given by gdp square rho p minus rho by 18 mu, which is 9.81 times 0.0001 cube, sorry, square times 4000 minus 1594 by 18 times 0.000965. And you'll get this as 12.8 millimeters per second. Okay, let's move on to the next question, where a spherical steel ball, very similar question. We just have to find out the ball. Okay, in fact, I'm going to leave this question out to you, where it is given that a spherical steel ball of 49 millimeter and density 8,500 kilogram per meter cube is dropped in a large mass of water. The coefficient of drag of the ball in water is given as 0.45. Find the terminal settling velocity of the ball in water. If the ball is dropped in air, find the increase in terminal settling velocity of the ball. I am going to leave this question to you. I'm hoping that you'll be able to solve based on whatever you have solved in class. And yeah, if you have any doubts, please let me know. I'll move on to the next question, which deals with free settling, which deals with week 7 problems, which has been dealt with free settling and inter settling, and flow through packed bed. So we'll just do one more question on uh, the free settling velocity. So in the question is given that 3 aluminum balls of density 2600 kg per meter cube, having diameters 2, 4 and 10 millimeter respectively, are dropped into a tank filled with glycerin at 22 degrees Celsius, whose density and viscosity is given. The terminal settling velocities are measured to be 3.2, 12.8, and 60.4 millimeters second. Compare these values with the values velocity predicted by Stokes' law for the drag force Fd equal to 3 pi mu Vd, which is valid for very low Reynolds number. Determine the error involved in each case and assess the accuracy of Stokes' law. So, in order to do this question, we need to find out we just need to find out the terminal settling velocity of the three balls, which is given by, let's say, ball A, which is ut is equal to, and we need to use the Stokes law. It is given. So, GDP square rho p minus rho by 18 times mu. Everything is same except for the diameter, which is 9.81. Yeah, so this ball A, which is 9.81 times 0.002 square times 2600 minus 1274 by 18 times 1. Okay, this value comes out to be equal to 3.017. Oh, sorry. This value comes out for me equal to 3.11 in millimeters per second. Similarly, if we do it for ball 2, it will be equal to 9.81 times 0.004 square, 2600 minus 1274 by 18. Oh, before I go on to the second ball, I need to assess the error for the first ball. So, percentage error in measurement is the value that is measured, which is equal to 3.2, which is given here in the question, minus 3.11 by the value measured times 100, which is equal to 2.9%. We have also been asked to find out, which we have also find out the Reynolds number here, which is rho ud by mu, which is 2600 times 3.11 into 10 raised to minus 3 times 10 raised to minus 4 divided by 18, and the Reynolds number here would be 0.008. Therefore, the error is actually very minimal. Now, if we do it for ball B, we'll get the settling velocity as 9.81 times 0.004 square times 2600 minus 1274 divided by 18, and this value will come out to be equal to 12.4 millimeters per second. If we calculate the percentage error, we'll get this as yeah, the value given here is 12.8. Therefore, we substitute that first. 12.8 minus 12.4 divided by 12.8 times 100. Again, we'll get around another percentage of approximately 3%. The Reynolds number calculated here will be 2600 times 0.0 sorry 0.0124 times 10 raised to minus 4 by 18. Sorry, this is not 18, this is 1. And this value will come out to be 0.065. Again, this value is considerably less than 1. Therefore, there is minimal error in calculation. Now, if we do this for the third particle of 10 millimeter, as shown in the question, or as asked in the question, we'll get the terminal settling velocity. If you find it out, we'll get it out to be 77.7 millimeters per second. Therefore, the percentage error would be equal to 60.4 minus 77.77 by 16.4, which is approximately equal to minus 28.7%, which is considerably huge, because the Reynolds number, which when calculated will come out to be 0.77, which is not less than not much less than 1. Therefore, there has been a considerable amount of error that has come up because the Reynolds number is close to 1. So yeah, these are the answers that you will get. We'll move on to the next question, where we have been asked to repeat the previous problem by considering the general flow of general form of Stokes law given as this. Therefore, when we do this, we'll get if we do the force balance, we'll get Fd is equal to the force of gravity plus the buoyant force, which is equal to the force of gravity minus the buoyant force, which is 3 pi mu dv plus 9 pi by 16 times rho s v square d square is equal to the force of gravity is basically rho times volume of the particle, which is given by pi d cube by 6 times g minus, yeah, this should be rho f times pi d cube by 6 times g. And we need to substitute the value of d for each case depending on what size we are using. If you do it right, you'll get the velocity for ball A as yeah, you'll be able to solve this and find the answer here. I'm gonna leave this calculation part up to you. What you're gonna find is the percentage error will increase for first and second balls, but third will considerably decrease because this correction has been introduced. Please do verify these values. I'm sure you'll get the answer. Um, if you have any doubts, I'll be staying on the call until 8 o'clock. So if you have any doubts, I'll be happy to help. Until then, yeah, I thank you for your time and attention.